So this is another way that we represent equilibrium. It's on an axis where you have the concentration of reactants and then like as time progresses how the reaction changes. So on the left, I'm going to do like what you learned in Gen Chem 1, which would have been like you get all the ingredients together for some cookies, you bake them, and at the end you have all cookies and you don't have any leftover eggs and sugar and stuff. And so what happens in that kind of reaction is that very quickly the reactants turn into products. You start at some number that isn't zero because you obviously have sugar and flour and eggs in your bowl. So you have some amount of reactants in there. And then it's kind of the steep descent. And then around in here, some of the reactants start having a hard time finding each other because there's so many products in there at that point. And so it kind of slows down a little bit. But eventually the idea is that you like run out of reactants because they've all turned into product. And then we'll also do these same exact ones and we'll do it for product. And so like a product, you don't have cookies when you've just put them in the oven. You got to wait for some time to happen. And so as soon as it all starts converting though, you end up with, you end up with a line and it kind of looks like that. So all the reactants have turned into products. And at the same time, all the products have turned into, have been made. And so instead of doing on two separate graphs, we often will put them on the same graph and they kind of have a look kind of like that. But that's what that graph means. It's just showing that products are being made and you didn't start with any because over here you didn't have any and then you have some. And over here you had some and then you don't have any. So you'll have to see them on the same graph. And if you have multiple reactants, they might not be lost at exactly the same point, but they might show differently, but they'd all have started maybe at that some point. Or maybe you had a little extra of one of their reactants. But I'm just saying they have like those same kinds of shapes and you would just have different lines that all started like over here for different reactants and same for the products. Now, in equilibrium, what happens is that the reactants can never get down to that point. And so if I go over here to my reactants and I pull this over a little bit, instead of them making their way to zero, what happens is they just kind of come down and then they just don't ever get to zero. We just always have some amount. This would be zero, and so there's some difference. And sometimes it can be like really high, like it can be like up here even. So you can have either option for those reactants. And then likewise the products, because not all the reactants are used, the products don't all get all the way to their maximum potential. And so the products that started as zero, remember, they don't quite get all the way up to where they're supposed to get. So again, often we put them on top of each other on the same graph. And I made this one just a little bit high, but there's still some distance that he could have gone up to if this was a 1-to-1 reaction. And he never made it. And so sometimes they look like that. And then sometimes they don't even cross in the middle. And then, so if I rewrite this one as reactants and products, then I'll have I could have it being like this where I just have some reactant and then I just have some product. So it can be that way too, but that's what these graphs are trying to show you is like, it's supposed to be, if the reaction were all the way, this curve would be coming down to there. And if the reaction was all the way, this line would go all the way up to there. But since it's at equilibrium, it doesn't quite hit the spot. It just kind of ends early. So don't be concerned if you see both of these kinds of graphs. That's what it means. It's just trying to show you generically how reaction is progressing.